Welcome to the video on molecular pharmaceutics, specifically nanotechnology and targeted drug delivery systems, or NTDS. This is unit number 1, part 1, for the second semester of M.Pharm in Pharmaceutics. I'm Dr. Krishna Yadav.
This video will introduce you to targeted drug delivery systems.
Targeted drug delivery systems, or TDDS, represent a sophisticated class of pharmaceutical formulations. Their goal is to selectively transport active agents to specific organs, tissues, or cell types, minimizing drug accumulation in non-target organs. The scope includes molecular prodrugs to particulate nanocarriers, aiming to alter pharmacokinetics, biodistribution, and control drug release over predetermined durations.
Conventional drug delivery systems face several limitations. These include poor bioavailability due to enzymatic degradation and first-pass metabolism, leading to reduced drug availability. They also cause fluctuating plasma levels, resulting in, quote, peak and valley concentration profiles, and lack selectivity, causing widespread side effects. Conventional medicine often follows a systemic, quote, carpet bombing approach. The core problem is the, quote, shotgun approach, leading to systemic toxicity, fluctuating plasma levels, and biological barriers, such as the blood-brain barrier. The lack of targeting results in uniform distribution and high off-target toxicity. The rationale for drug targeting addresses the core problem of conventional drugs. Most conventional drugs distribute uniformly throughout systemic circulation, with only a small fraction reaching the pathological site. TDDS offer the solution by restricting drug distribution to the site of action, enhancing efficacy, and reducing systemic toxicity. This improves patient compliance and therapeutic outcomes. Targeted delivery uses sophisticated formulations to selectively transport agents to specific sites, minimizing off-target accumulation. The goal is to alter pharmacokinetics to maximize the area under the curve at the target site. This involves temporal control or sustained release and spatial localization. TDDS offers significant clinical advantages. They allow for dose reduction by concentrating the drug at the active site, bypassing biological barriers like the blood-brain barrier. They protect labile drugs from enzymatic degradation and provide co-delivery capabilities for multiple therapeutic agents simultaneously. An ideal targeted system requires several key characteristics. These include biocompatibility, high loading capacity, stability, specific targeting, controlled release, and evasion from clearance by the reticuloendothelial system, also known as stealth. Comparing conventional versus targeted delivery highlights the benefits of TDDS. Targeted delivery achieves site-specific localization, requiring a low dose and resulting in minimal toxicity. It allows for controlled, sustained, or triggered drug release, is engineered to traverse barriers, and leads to higher patient compliance. The evolution of drug targeting spans a century of innovation, from Paul Ehrlich's 1906 magic bullet vision to the discovery of liposomes in 1965. Key milestones include the description of the EPR effect in 1986, the first FDA approval of a pegylated liposome in 1995, and the global deployment of LNP-based mRNA vaccines in 2020. Chapter 2 focuses on the objectives and design requirements of TDDS. The primary therapeutic objective is to maximize the drug's intrinsic activity while minimizing limitations by improving solubility, enhancing stability, and optimizing the absorption profile. A key goal is also to alter the pharmacokinetic profile to ensure a higher AUC in the target tissue compared to normal tissues. The ideal TDDS has several characteristics that serve as benchmarks for design excellence. These include biocompatibility, high loading capacity, stability, specific targeting, controlled release, and evasion of clearance to allow sufficient time for target accumulation. The ideal carrier must exhibit several key characteristics. It must ensure biocompatibility, controlled release without premature dose dumping, and specificity via lock-in key recognition. Additionally, it must provide high loading capacity, stability in circulation, and stealth to evade RAS clearance. The success of a targeted system relies on synergistic selection of the drug, carrier, and target. Drug selection requires high potency and stability. Carrier selection depends on the drug's physicochemical properties, with lipid carriers for hydrophobic drugs and polymeric systems for charged molecules. Target selection requires targets to be overexpressed on diseased cells to ensure selectivity and minimize off-target effects. Chapter 3 covers the fundamental concepts of drug targeting, beginning with drug-target interaction mechanisms. These involve physicochemical processes, such as non-covalent forces, hydrogen bonding, van der Waals forces, and electrostatic interactions. Active targeting works like a lock and key system, where a ligand acts as the key, fitting specifically into a receptor lock on the cell surface. Target site characteristics and accessibility are crucial for successful drug delivery. Critical factors include vascular density, rate of blood flow, and the presence of stromal barriers. For instance, solid tumors often have high interstitial fluid pressure, which creates a significant barrier to drug penetration and must be accounted for in system design. Specificity is the carrier's ability to distinguish between target and non-target environments. Selectivity is the ratio of drug accumulation in the target versus non-target tissues. Affinity describes the strength of binding between a single ligand and its receptor. Avidity refers to the accumulated strength of multiple binding interactions, known as multivalency, occurring between a carrier with multiple ligands and a cell with multiple receptors. This diagram provides a mechanistic distinction among specificity, selectivity, affinity, and avidity in molecular interactions. Specificity is like a lock and key precision. Selectivity shows a preference among competitors. Affinity illustrates the strength of a single interaction, and avidity represents multivalent cooperative binding for a very high overall affinity. Drug localization, accumulation, and retention are essential processes. Localization is the drug's arrival at the target site, accumulation is the buildup of concentration, and retention is the ability to remain at the site for the therapeutic effect. Successful systems must achieve localization, often via the EPR effect, or ligand binding, and retention to prevent washout. Chapter 4 focuses on the targeting hierarchy, or the levels of drug targeting. Drug targeting operates across multiple biological scales, determining the precision required in carrier design. This hierarchy is classified into organ and tissue level, cellular level, and subcellular, or organelle level targeting. This illustration visualizes the hierarchy of drug targeting, moving from the organ and tissue level to the cellular and subcellular levels. Each progressive level demands greater precision and sophistication in the design of the drug delivery system. Organ and tissue level targeting, or first-order targeting, delivers drugs to a specific organ like the lungs or liver. For lung targeting, particles larger than 7 micrometers are mechanically trapped. For liver and spleen targeting, particles between 100 to 200 nanometers naturally accumulate due to RAS filtration. Cellular level targeting, or second-order targeting, delivers drugs to a specific cell type within the target tissue. The challenge is differentiating between cell types in the same organ, such as Kupffer cells and hepatocytes. The solution requires active targeting with ligands that bind to unique cell surface receptors. Subcellular or third-order targeting is the pinnacle of precision, directing drugs to specific organelles. Examples include targeting mitochondria for pro-apoptotic drugs, the nucleus for gene therapies, or the cytoplasm for RNA therapies. This requires overcoming intracellular barriers, like endosomal entrapment and lysosomal degradation. Chapter 5 introduces the primary targeting strategies. They are broadly classified into passive, active, physical, and dual targeting. Passive targeting relies on pathophysiology like the EPR effect. Active targeting uses ligand-receptor interactions. Physical targeting employs external fields, and dual targeting combines strategies for enhanced efficacy. Passive targeting leverages inherent physiological conditions and carrier characteristics for drug localization without specific homing ligands. Key principles rely on natural biodistribution and exploiting disease pathology, such as leaky vasculature, known as the EPR effect. The mechanism relies on physicochemical properties like size, charge, and hydrophobicity. Active or ligand-mediated targeting involves conjugating a homing ligand to the carrier surface. This ligand specifically binds to receptors overexpressed on target cells, enhancing retention and cellular uptake. The key advantage is significantly increasing cellular internalization once the carrier reaches the tumor microenvironment. Physical and stimuli-responsive targeting uses carriers responsive to external triggers, like magnetic fields or light, or internal biological cues like pH changes. Examples include magnetic guidance, ultrasound activation, photothermal therapy using laser light, and pH-responsive release in acidic tumor environments. Chapter 6 delves into passive targeting, focusing on its biological and pathophysiological basis. Passive targeting relies on physiological differences between healthy and diseased tissues. In pathological states, the disruption of vascular integrity by permeability factors allows for the selective accumulation of macromolecules or nanoparticles at the target site. The enhanced permeability and retention, or EPR, effect is the cornerstone of passive tumor targeting. Discovered by Maeda and colleagues, the EPR effect consists of two complementary phenomena: enhanced permeability and enhanced retention. This diagram illustrates the EPR effect in action. In normal tissue, the vasculature is tight, preventing nanoparticles from leaking out. In tumor tissue, the leaky vasculature, combined with poor lymphatic drainage, allows nanoparticles to accumulate and be retained, maximizing the drug concentration. The efficiency of passive targeting is strictly governed by physicochemical parameters. Key size considerations require particles to be less than 200 nanometers to exploit the EPR effect, but greater than 10 nanometers to avoid rapid renal clearance. The optimal size range is typically 50 to 150 nanometers. Neutral or slightly negative surface charges are preferred, as highly charged particles are rapidly cleared or are toxic. Finally, hydrophilic coatings such as PEG are essential for providing, quote, stealth properties to prolong circulation time. Passive targeting offers advantages, including simpler manufacturing and clinical validation through drugs like Doxil. However, limitations are significant. The EPR effect is often heterogeneous and less pronounced in human tumors than in animal models. The clinical reality is that only about 0.7% of the administered dose reaches solid tumors, emphasizing the need for improved strategies. Chapter 7: Transitions to active targeting. Active targeting involves modifying a drug carrier with a specific affinity ligand. The goal is to enhance accumulation and uptake by target cells, operating on a specific lock-and-key principle. Crucially, active targeting does not usually increase the total drug delivered to the tumor, which is governed by passive accumulation, but rather enhances cellular internalization once the carrier is nearby. This graphic demonstrates the synergy between passive and active targeting. Nanocarriers first rely on passive targeting via the leaky tumor vasculature and poor lymphatic drainage to accumulate in the tumor microenvironment. Then, the surface ligands engage in active targeting by binding specifically to overexpressed receptors on the tumor cell surface, triggering internalization. We use various types of targeting ligands. Antibodies offer high specificity, exemplified by trastuzumab targeting HER2 receptors. However, they are large, immunogenic, and expensive. Peptides are smaller and less immunogenic, like the RGD peptide, but they often have lower affinity than antibodies. Aptamers are oligonucleotide sequences that fold into 3D structures. They are non-immunogenic and chemically synthesized, but susceptible to degradation. Small molecules, like folic acid, are inexpensive and well characterized. However, they generally have lower specificity compared to antibodies. Active targeting exploits the overexpression of specific receptors on diseased cells. For example, the folate receptor can be overexpressed up to 100-fold in cancer cells. The transferrin receptor is upregulated 5 to 10 times to import iron. The HER2 receptor is overexpressed 20 to 100-fold in certain aggressive breast cancers. This illustration shows how receptor overexpression facilitates active targeting. The diseased cell on the left has a high density of receptors, leading to massive ligand binding and internalization. The healthy cell on the right has low receptor density, resulting in minimal binding and reduced off-target toxicity. Once the ligand binds to the receptor, the carrier must be internalized into the cell. This process, known as cellular internalization, brings the drug into the cell via endocytic pathways. Following internalization, the carrier must achieve endosomal escape to avoid degradation by lysosomes. This escape is critical for therapeutic agents that need to reach the cytoplasm or nucleus. This graphic details the three primary endocytic pathways. Clathrin-mediated endocytosis, often used for nutrients like cholesterol, is the most common. Caveolae-mediated endocytosis uses lipid rafts, and clathrin/caveolae-independent endocytosis or macropinocytosis is used for bulk fluid uptake. Understanding these determines optimal carrier design. Active targeting offers advantages, including enhanced cellular uptake, the ability to target metastases, and bypassing multi-drug resistance pumps. However, major challenges exist. The binding site barrier means high-affinity particles bind peripherally and cannot penetrate deeper into the tumor. Other issues include manufacturing complexity and the potential immunogenicity of ligands.
Thank you for watching this video. Please share and subscribe to my channel. Please share and subscribe to my channel.